let us start lecture 24, and the course is phase diagrams in single component and binary systems. And today's topic will be the treatment of multi-component systems, and we will be taking mixing of ideal gases to start with. As I have informed that later this mixing of ideal gas, that concept what we develop, that can be taken to condensed systems also. Now, in the last lecture we talked about standard state considering a closed system, fixed composition, constant temperature, and then we started looking at change in free energy or the molar free energy as a function of pressure, and then we introduced a concept called standard state. And the standard state free energy is denoted as G naught with a small 0 as a superscript at any temperature when the pressure is 1 atmosphere. That is basically standard state. With reference to standard state, we calculate the difference of free energy values. Now, when we talk about the assigning standard state, we have also talked about some of the values, like in electrochemistry we talk about the molar free energy of hydrogen ion at 298 Kelvin, 1 atmosphere pressure is considered as 0. Similarly, when we talk about aluminum in solid condition at 298 Kelvin, 1 atmosphere pressure, that is there the enthalpy is considered as 0, 0 is assigned to that, which is also a standard value. Here 298 Kelvin has a meaning, because we are assigning that 0 value at a particular temperature when the pressure is 1 atmosphere. But any other temperature, any other phase, if I consider that time, that value cannot be assigned as 0. For example, 298 Kelvin, 1 atmosphere pressure, the standard enthalpy value of liquid aluminum or solid or vapor gaseous aluminum, they are not 0. Okay. So, that helps us to calculate the difference in enthalpy values. Okay. In fact, whenever we see that 0 superscript 0 on any state standards, any state variable like Gibbs free energy or enthalpy or even entropy, we do not have to mention 1 atmosphere, that is considered as 1 atmosphere. So, that is what we have learnt in the last lecture. Now, today we will talk on mixing of ideal gases. So, we will talk on So, when we talk about mixing of ideal gases, we need to understand the composition. Okay. So, let us say in a closed system, 3 components, 3 ideal gases, A, B and C. Now, all those cases I have Na mole, Nb mole and Nc mole. These are the number of moles of those gases. Then I can calculate the composition of the each of the components. I can calculate like this, which is in terms of mole fraction of A. I can write it as Na, Na plus Nb plus Nc. So, that becomes mole fraction of A. Similarly, like that way, any component, let us say and that is denoted as Xa. So, Xi, that means let us say there are many n number of components, and if I try to calculate the mole fraction of ith component, then I can write it as Ni summation of Ni 1 to n. Okay. So, that becomes my mole fraction. Now, once we know the mole fraction, then we can also find out, let us say these 3 gases are there and each gas will have some sort of contribution to the total pressure of the system, since we have considered closed system. Okay. We have a particular law that is called Dalton law of partial pressure. Okay. So, what it see this partial pressure, what is this? So, each of the component gases, what will be their contribution towards the total pressure of the system. Okay. If I want to learn that, so it's that time we have to use the Dalton law of partial pressure. It says that if we consider the system is a closed system, fixed temperature. Okay. So, at a temperature the volume is V prime. Okay. So, then I can find out what will be the partial pressure contribution to the total pressure. And this Dalton law of partial pressure, it says that P, which is the total pressure of the system, should be equal to P I P A plus P B plus P C, and here the partial pressure are written in terms of a lower case of P. So, those are the partial pressures of individual gases. Okay. So, those are the partial pressures. It's basically if I consider nth, so it's become. Okay. So, this is the Dalton's law of partial pressure. Now, if I try to look at this, we can actually relate the partial pressure with reference to the composition of each component gases. Okay. Each component gas. In fact, if I try to see, this is basically total volume, and this is at temperature T, then I can find out P A P, a total pressure is nothing but let us say there are 3 component gases, Na plus Nb plus Nc, the total number of moles into RT by V prime. Okay. So, this is equation of state. Now, so this is total pressure, P is the total pressure. Okay. Now, if I try to calculate P A, since all are ideal gases, the mixture of ideal gases is also ideal. So, I can write Na RT, since the ideal gas will contain into that total volume V prime. So, I can write this. So, from here I can write P A by capital P, which is the total pressure. So, then it becomes Na divided by Na plus Nb plus Nc with, so this RT V prime, RT V prime. So, these two things will cancel. So, this becomes X A. So, I can write P A equal to X A total pressure. So, more generic term would be if there are number of n number of components. So, then I can write P I equal to X I P. So, this is nothing but the Dalton's law of partial pressure. So, this is basically what it states. So, that in a mixture of ideal gases, the partial pressure of a component gas is the product of its mole fraction and the total pressure of the gas mixture. Fine. Now, from here if you see, I can have one more equation which is should be equal to 1. So, this would be needed later on, but at least we know that if we add up all the mole fractions in a closed system, I should get 1. Okay. So, that is one other important equation. So, we have 3 important equations, this one, second, and this is third. Okay. 3 important equations we are getting. Now, let us get into the mixing part. When we talk about mixing, mixing of ideal gases, then we should bring in partial molar quantity. Fine. Now, let us say Q is a generic thing. Q is basically the extensive property of a quantity of a particular quantity of a kind of arbitrary quantity of the mixture. So, remember this is extensive property of a quantity of the mixture, and this quantity could be arbitrary. It can be 1 mole, it can be 2 mole, it can be 3 mole. Fine. So, then let us say this is Q. So, then I can find out, and let us say there are n number of component gases, all are ideal gas. So, then I can write Q bar with a I, that ith component partial molar quantity should be equal to okay. And this we already have understood with the reference to G. If we recall, chemical potential of ith component, which is nothing but G I bar, which is nothing but partial molar quantity, partial molar free energy, gives free energy, and this is also called chemical potential of ith component in a mixture. When we talk about mixture, it is basically in a phase. So, that mixture is a homogeneous mixture. Okay. So, that can be written as delta G delta Ni Pt Nj. So, that means all other components are fixed. So, this becomes that partial molar gives free energy. Okay. So, from that it is coming. So, this can be applied. So, here it is only for G, we can actually take it down to partial molar quantity of V, which is I, should be equal to that partial molar volume of ith component can be written as del V del Ni Pt Nj. Okay. I can write that. Okay. So, now here one more important aspect is, remember that when we write this quantity Q is the total value of extensive property. It is not molar, because I do not know what is the number of moles present there. So, the number of moles could be N1, N2, N3 like that, Ni and then it can go to Nj, okay, the n number of quantity, and J could be, so this n number of component gas, and each one has got certain moles, okay, of that particular gas. So, it could be 10 mole, it could be 100 moles, it could be 1 mole also, but when it becomes 1 mole, that can be expressed in terms of mole fraction. So, how? So, let us, we know that Gibbs-Duhem equation one of those Gibbs-Duhem equation writes like this: G equal to N 1 mu 1 N 2 mu 2 like this. So, let us say I take 1 mole. So, then I can write, this is my total free energy. So, I can write for 1 mole G by summation of N 1 by N y mu 1 plus N 2 N I mu 2 like this. So, it can go down to, that time it becomes, let us say this becomes G m, this term can become G m when m is the molar quantity, should be equal to x 1 mu 1 plus x 2 mu 2 like this. I can write this. So, hence this Q is the extensive property of the total extensive property of that mixture. So, now we see that volume can be expressed. In fact, enthalpy can also be expressed like that. So, because all are extensive property. Now, considering this, I can do a treatment. What is the treatment? So, let us do the treatment. So, we know I can write generic equation, whether it is a closed system, varying composition, or open system, and where matter can exchange with the surrounding, between the surrounding and the system. So, the generic equation becomes delta G equal to V dP minus S dt plus mu I dNi, where I can write 1 to n I can take, fine. So, this is my generic equation for Gibbs free energy for the system. So, then if I write this, constant temperature and constant composition. See, if I do that, so then I should get V, okay, and V is the total volume of the system. Now, after that, if I further treat Ni dg dNi T composition. So, I am fixing composition as well as temperature, and then I am fixing, now when I am fixing Ni, then P, T, Nj, all the other components are fixed. So, this would become del V del Ni P T Nj. Okay. So, all other components are fixed. So, this becomes Vi bar. We know that the partial, this becomes, this is nothing but partial molar volume of ith component in a mixture. Since G is a state function, so I can write d Ni dg, there is a mistake, please correct this, this should be P, please correct that. it should be P, because from this, if I have to write this, then temperature and compositions are fixed. So, with reference to pressure, we are trying to see the free energy change. Okay. And then the second level we are doing Ni. Okay. So, this becomes, I can, this is the one what we have seen. I can write it as I can write this, since G is a state function. Okay. So, this equal to B I bar, and we know that dg dni pt nj is nothing but G bar I. In fact, here instead of this I can write it as G I bar. So, I will tell you why I am writing with reference to G I bar. You can also convert into mu and then do the entire treatment with reference to mu, but G I bar will be helpful to understand. Now, this is this. So, that means this part I can write it as equal to V I bar. So, this becomes so this is an important equation. So, d G I bar equal to V I bar dP. From this we can actually get to another important equation, which is G I bar equal to G I naught plus R T ln xi plus R T ln p. So, this equation we can get, and from there only we can calculate the situation when we mix together, what will be the enthalpy contribution after mixing, what will be the free energy contribution after mixing, as well as we can calculate what will be the entropy contribution when we mix multiple ideal gases. So, the next class we will try to solve this, how to get to G I bar, G I naught plus R T ln xi, R T ln p, where G I bar equal to is nothing but standard Gibbs free energy of ith component when it is pure, and 1 atmosphere pressure. Okay. Xi is basically the mole fraction of ith component in the mixture, and P is basically the total pressure of the system. Fine. And remember, in this case we have considered a kind of a generic equation, but when we try to solve this, what will be the mixing enthalpy, mixing free energy as well as mixing entropy, we will get back to a closed system. Okay. So, the next class our job would be to prove this equation as well as to get on to calculate values of enthalpy of mixing, gives free energy of mixing, and delta S mixing. See, all those three will try to calculate for ideal gas mixture, and this mixture is homogeneous mixture. Fine. So, let me stop here. Thank you very much.